All right, so we've got these things called complex numbers. In the next video, I'll show you how you can visualize these as points in a plane, which is, it can be very, very helpful. But to do the algebra, we don't absolutely have to do that. We just recognize that anything that is of the form real number plus other real number times I is going to be a legal complex number. And we need to figure out how algebra works. And as I said at the end of the last video, the key thing is just use the usual rules of algebra, and that whenever you see an I squared, simplify it to -1. So let's add complex numbers together. It's going to feel a bit like adding polynomials. So if you imagine I temporarily is x, if I asked you to add 3 plus 2x and 5 plus 7x, you'd group the stuff that didn't involve x. And so here we're going to group the stuff that doesn't involve I. That's just reordering this is just going to reorder the sum. That's totally legal. Adding can be done in any order. That's a fundamental property of addition. And is this definitely the same thing? And then I just actually do the 3 plus 5. Now I'm going to factor out the I out of 2 plus 7, just as if you were factoring out an x out of here. It really is. If you just rewrite this with x instead of I, it will be standard algebra. The next stuff will be a little bit new. But this is very, very much like very simple polynomial algebra, where we just added the real parts, in other words, and we added the imaginary parts, right? So a little bit of a shortcut here, whoops. Or let's say the punchline is when we add the real parts and separately add the imaginary parts. They don't interact at all. Pretty soon they will, in a very interesting way, but right now they don't. Subtracting, super similar. I'm just going to regroup. So notice that minus sign needs to distribute. Okay, so that's minus sign goes on the 5, and then the 2i was with a plus, but that minus distributes over the 7i. So when I rewrite it, that's going to be a minus. Okay, watch out for that. People are still having trouble with that sometimes. So that's going to be a -2, and then I'll factor out the I again. And so that's -2 minus 5i. Notice, if somebody said, just look at the real parts and subtract those, I would totally get the real part of the answer. And if then somebody said, just take the imaginary parts, the 2 and the 7, and do the subtraction. 2 minus 7 is -5. So very similar to what we had before. If you want a slightly faster way to do this, subtract the real parts and subtract the imaginary parts. Once again, so for addition and subtraction, the real parts and the imaginary parts are working in parallel, do not interact at all. Multiplication is where they really start interacting and where stuff starts to get kind of deep. Okay, so let's do this. I'll display this. Okay, here I'm going to FOIL it all out. Again, the first steps are very much similar to if this was an x and this I over here was an x. The first steps are almost identical with an I instead of an x, but there's going to be one really crucial step. So if I FOIL it, I'm going to get 3 times 5 is 15. That's just adding the firsts, okay? Then the outer is 3 times 7i. That's just 21i, just absolutely standard. And then the inner is going to be 2i and a 5. That's going to be a 10i. And then the last thing is going to be the lasts put together. That's a 2i times 7i. So the 2 and the 7 is a 14. And guess what I get? I squared. So far, so good. This is absolutely, completely true. And it's identical to what you would get if I were just a variable like x and these were polynomials. But the key thing is that I squared simplifies. Never, ever leave an I squared alone. Always turn it into a -1. Okay. In other words, let's see if I can highlight all this. That's just -14. And hey, wait a minute. Okay, now let's collect. So now the last step is, again, very much like what you would get if the I were just an x. These guys both have an I in them. I want to combine those together. And the 15 and the -14, even though they came to us in rather different ways, they're both real numbers. So the 15 and the -14 actually cancels down to just a 1. That's interesting. It's a little unexpected. And then I'm going to group these things together. 21 of something plus 10 of something. So 21 apples plus 10 apples, that's 31 apples. So every step except going from I squared to -1 was it was exactly analogous to what you do with very simple kind of polynomial manipulation, which you guys are good at. Okay, so that's the secret. And a lot of the magic of complex numbers, and trust me, there's a lot of magic. You won't see the whole full magic for a while, but there's so much magic, and it really comes from this kind of calculation where you get this kind of unexpected cancellation and kind of regrouping from the product. Okay, we'll practice that. Just wanted to get you familiar with it. Dividing, okay, that is tricky, right? You can just go ahead and write that and be like, okay, that's a thing. Okay, kind of. That is a thing. But what I claim is there's a standard way to actually rewrite it as mystery real part plus mystery imaginary part times I. In other words, to put it into standard form, right? Notice everything here, it wasn't really hard, although it was getting a little more complicated here, to put it into an a plus bi form, where I can tell you the real part is 1, the imaginary part is 31, for example. Here, this does actually have a standard form. It has a well-defined real part and imaginary part, but what are they? Okay, and that's where this is very similar to rationalizing the denominator. Let me remind you real quick. We kind of had to do this a little bit. We did it more in the geometry semester, actually. If you had something like this, how the heck do you simplify that? And the claim is you can get it so that even though there will still be a root 2 in the final answer, it won't be in this really awkward place in the denominator. Denominators are complicated places. Why overcomplicate it by having a root in it if it's not necessary? Okay. And actually, let me, that's not a great example. Let's say, let me make that a 6, just so it's not kind of a little bit special. Okay. And so let me remind you of the trick here. It's been a while. What we do is the only way we pretty much ever simplify a fraction is we multiply by 1. And we do this clever thing, which is where we multiply by 6 plus root 2 over itself, right? The absolute key thing is that this is just the number 1 written in a very, very clever way. Well, why clever? Why is this not going to just make things more complicated? What we do is we look at the bottom, right? This is using the all-important identity. Ooh, that's not going to like that, is it? The all-important identity that a minus b times a plus b is a squared minus b squared. The difference of squares, that's a cool factorization, but it's also a cool simplification of this kind of product. And we're purposely putting in that kind of product. So again, you might be wondering, wait, where'd the i's go? But I want to show you this as an example with real numbers, and then we'll see that the same exact thing is going to work with I. Because this should be a little more familiar, even though I know this is pretty rusty as well. Okay, so on the bottom, what are we going to get? We're going to get 6 squared. Okay, that's a nice number, 36. And the key is that we're going to get minus b squared, and that kills the square root. That's minus 2. Okay. Now, on the top, nothing particularly nice happens. This doesn't magically make all roots go away, but it does make the roots just go into the numerator. And so I'm going to get 30 plus 5 root 2 all over 34. And if I want to, I can separate that out into a really perfectly nice rational number and then sort of separate out the root 2 part. And that's very nice to know. Okay. It kind of says, okay, the root 2 does still have to be in there, but it's in a little bit more tame kind of location. Okay. So let me show you, go back to here and show you how that exact same thing works here, and it's even a little bit slicker. Okay. We're going to just recopy that, and we're going to multiply it by 5 minus 7i over 5 minus 7i. And I'm going to give a name to that in a second, but we don't need the name to see how it's going to work. Okay. Okay, I don't think I wanted to really copy that. So here's the cool thing. We're going to use this same thing again, but we're going to get a very interesting answer. We're going to get 5 times 5 is 25. That's easy. Then this says minus b squared. Okay, what is that? Minus, and then 7i, the quantity 7i squared. And we'll worry about the numerator in a second. It's going to be a little complicated, but it's okay. Okay, wait a second. 7i quantity squared. Let me just do a little work inside here. That's just squaring both of those guys. Hey, I squared. I know what that is. That's minus 1. Oh, wait, the minus 1 cancels this guy. Whoa. right? Actually, let me actually write that explicitly. That's really cool, and it's actually a shortcut that you can memorize if you want. You'll always get, when you do this trick, whatever this is, a plus bi, you'll always get a squared plus b squared on the bottom. No exceptions, okay? So that's pretty cool. It's not a complicated number, and it's real. No I in the denominator. That's very cool. Okay, now what are we getting on the top? That's where the complexity happens, but it's better than having the complexity in the bottom, okay? So on the bottom, ooh, God, 49 plus 25, 74, just a real number. And now I got to do the multiplying thing, right? So not surprisingly, to understand division, you're going to at least have to understand multiplication. All right, so 3 times 5 is 15. I'm going to do it a little quicker. 2i times 5, it's going to be really, really similar to this one because this was with a minus sign, right? 2i times 5 is still plus 10i. Ooh, but 2i times minus 7i, that's going to be, 3 minus 7i is minus 21i. Oh, I'm doing it in the wrong order. Let me do it in the same order I did it above, yeah. Okay, so that's just changing sign here. Okay, and then 2i times minus 7i minus 14i squared. But that I squared is a minus 1, and that just switches this guy. We're almost done. Let me put it down here. 74 in the denominator, and you got a 29 and then minus 11i. And then we often want to just, like that very last step I did with the root 2 there, we're going to say, so we get a moderately complicated answer, and definitely not something that's easy to just guess, right? This is where it gets to where I wouldn't advise trying to do this in your head, okay? The 74 was not super obvious, although I do think it's a very pretty fact. And the exact combination with the minus and the blah, 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 it's a little bit funky, okay? So what do we get? The real part of this quotient of complex numbers is 29 over 74. The imaginary part is minus 11 over 74. A very interesting, kind of unexpected answer, but very, very worthwhile. Okay, so I'm going to show you in a third video, I'm going to show you a very, very brief introduction to how this works geometrically.